Hello, this is the fourth video on honors linear algebra and multivariable calculus. In this video, we're going to talk about Rn as a vector space. In the previous video, we talked about Cartesian product of sets, and Rn is the set of all n tuples of the form x1, x2, xn, where xj's are all real numbers. Each of these elements is called a vector, and what we're going to do is we're going to define an operation between these vectors. So we add two vectors, x1 through xn and y1 through yn, by just adding them component wise. In other words, we add the first components, we add the second components, and so on. Each of these vectors can also be rescaled by a real number. So we can take a vector, we can multiply it by a scalar, and the way we do that is we multiply each of the components by that scalar. So there are interpretations of these two operations, the addition and vector addition and scalar multiplication. So let's say you have two vectors in R2. So the first one is x1 and y1, and we always draw the vectors from the origin. The second one would be x2 and y2. So when we add them, we'll have to add x1 to x2. So this is x1 and this is x2. So we'll have to take x2 and we're gonna have to move x1 units to the right. So we take this portion and we put it right here. So x1 units right here. So this would be x1 plus x2. So we have to go this much to the right. And then the same thing on the other side. So in other words, we have to take this same vector and put it right here. And we are going to obtain a parallelogram. This would be the sum of the two vectors. So it's the diagonal of the parallelogram that these two vectors form. This is, if this vector is u and this vector is v, the diagonal would be u plus v. Scalar multiple can also be interpreted geometrically by taking a vector, not changing its direction when c is positive, and rescaling its length. So if this is u, then c times u would be something like here, something like this, or it could be on the opposite side, depending on whether c is positive or c is negative. So these are the interpretations geometrically. This vector addition and scalar multiplication satisfy the following properties. So these are algebraic properties of addition and multiplication. The first one is called closure. If you take two vectors, when you add them, you get another vector. If you take a vector and you multiply it by a scalar, you get another vector. So sum and scalar multiple of one vector would be also vectors. So this property is called closure. The second property is associativity, which is really just two different properties. For every xyz in Rn, if you take three vectors in Rn, you have associativity for addition. X plus y plus z is the same as x plus y plus z. And ab times x is the same as a parentheses bx. So this is associativity. And these are very easy to check. Commutativity. If you take two vectors, when you add them, you can add them in any order. So x plus y and y plus x are the same. And these properties all follow from properties of addition and multiplication in real numbers. Next property is additive identity. So if I take a vector x and I add the 0 vector, if I take x1 through xn and I add the vector which all of the components are 0, I would end up with x1 plus 0 all the way to xn plus 0, which is the vector x1 through xn. So that's called additive identity. Additive inverse is just negation. So for every vector x, there is another vector y that when you add them, you get 0. So if you take the vector x1 through xn and add it to negative x1 through negative xn, you end up with 0 in all coordinates. And next property relates addition and multiplication. It says you have the distributive law. So if you take a plus b and multiply it by x, you get ax plus bx. And also you can distribute scalar multiplication over vector addition. So a times x plus y is ax plus ay. These are, again, easy properties. Both follow from properties of addition and multiplication. And finally, we have the multiplicative identity. If you take a vector x and multiply it by 1, it means you're multiplying each of the components by 1, which means you're not really changing your vector. These 7 properties are called vector space properties of Rn. And this is often stated as Rn is a vector space. Sometimes elements of Rn are referred to as points. That's really just for visualization and conceptualization. Not really anything. Math doesn't really change. The math does not change, but this is only for conceptualizing these objects. When elements of Rn are seen as points, the 0 vector is referred to as the origin. So let's talk a little bit about geometry of them, and for that we need to look at the coordinate axes. So in R2, we know that we can represent every element of R2 by a point on the plane. That's something you have seen starting from algebra. So any point of the form x comma y, any element of R2 which is going to be a pair of numbers x comma y can be represented by a point on a plane. So you can take a point here, maybe 2 comma 1, and that would be a point which is a geometric object, but algebraically you can represent that with a pair of numbers. If we look at R3, then elements of R3 can be represented by points in a 3-dimensional space. To do that, we need 3 axes. We need x-axis, we need y-axis, and we need the z-axis. These 3 axes must satisfy the right-hand rule, which means if we look at if we point our thumb in the right hand in the direction of the z-axis, our hand would close from the x-axis to y-axis. So point your thumb in the direction of the z-axis, and you should be able to close your hands from x-axis to y-axis, from the positive x-axis to positive y-axis. The coordinates of each point in the 3-dimensional space can be found by dropping perpendiculars to the axes. So we take a point P, we drop perpendiculars. Whatever numbers that we get here are going to be the coordinates. So in this example, 2, 3, 4 are the coordinates of this point P. The set of all points with positive coordinates is called the first octant. So all of the points x, y, z in R3 such that x and y and z are all positive, this is called the first octant. So there are 8 octants. If you take the 3 axes, they divide the entire space, these 3 planes containing xy axis, xz axis, and yz axis. They create 8 different regions, and these 8 are called octants. One of them is the one that everything is positive. X, y, and z are all positive, and that one is called the first octant. There are 3 planes, each containing 2 of the axes, 2 of the x, y, and z axes. Each of the 3 xy, xz, and yz planes is called a coordinate plane. So if I draw a diagram for this, so this is x, y, and z. You see there is a plane at the bottom. This plane is the xy plane. There is a plane that contains x and z axes. So that would be the xz plane, and of course there's also a negative side of it and also the bottom. So it's the entire plane. And there's also a plane that contains y and z axis. So this plane is called the YZ plane. These three planes are called coordinate planes. Okay, so the last thing we're going to talk about in this video is the distance between 2 points. So if you take 2 points in three-dimensional space, then the distance between them can be evaluated using this Euclidean distance formula, or the distance formula that you have seen. Okay, let's prove this one. So let's take 2 points. So we're going to take a point P, which is x1, y1, z1, and we're going to take a point Q, which is x2, y2, and z2. And I want to find the distance between these 2 points. So what I'm going to do is I'm going to create a right triangle. So I'm going to take P and drop a perpendicular from P to the xy plane, and I'm going to call that P prime. And I'm going to take this point Q and drop a perpendicular again and get a point Q prime. So take P prime and Q prime to be the projections of these 2 points P and Q onto the x and y plane. Now, when you project a point to the xy plane, the z coordinate becomes 0. So z coordinate becomes 0 for this one, and for Q prime also the z coordinate becomes 0 because we are on the xy plane. X coordinate and y coordinate do not change because we dropped a perpendicular. So this would be x1 and this would be x2, y1, and this would be x2 and y2. So now let's see what happens. So we have a line between a segment connecting P prime and Q prime, and that's parallel to this line. So I'm going to draw a line parallel to P prime, Q prime, and let me call this one H. So in triangle PQH, I can say that PQ squared, it's a right triangle, is equal to HQ squared plus HP squared. And the reason is the Pythagorean theorem. So this is by the Pythagorean theorem. Okay, now PH is the distance, is the vertical distance between P and Q. What does that mean? It means it's the difference of the z coordinates. So PH is the absolute value of z1 minus z2. Now what about QH? We have a rectangle right here. So QH and Q prime P prime are the same. So QH, HQ is the same as Q prime P prime. But if you look at Q prime and P prime, they are now in 2 dimension. We know the formula for distance in 2 dimension. And that's again another Pythagorean theorem. So this one is square root of x1 minus x2 squared plus y1 minus y2 squared. Now take these two, plug it into the formula for PQ. PQ squared is going to be HQ squared, which is z1 minus z2 squared plus HP squared, which is z1 minus z2 squared plus HQ squared, which is x1 minus x2 squared plus y1 minus y2 squared. And just take the square root of both sides. So PQ, which is the distance between P and Q, would be square root of, and I'm going to rearrange these to match the formula that they gave us, and we get exactly what we wanted. And that brings me to the end of this video. So I will see you in the next video.